You wanted a clock that never needed setting, but what started as a simple desire for convenience has escalated into a critical infrastructure shift underpinning the entire AI revolution. We often treat timekeeping as a trivial consumer annoyance or a background utility we don't think about until daylight saving changes mess up our schedules. But in the world of distributed artificial intelligence, precise synchronization is not just convenient, it is the absolute bedrock upon which model training reliability and data integrity are built. Without atomic-level clock precision across thousands of nodes, massive clusters drift into garbage states, halting expensive training jobs that cost tens of thousands of dollars per hour to run. The core engineering truth that most developers miss is that synchronized time is physically impossible at scale, yet absolutely required for our software to function. This creates a fundamental category mistake, where we build systems on assumptions about physical reality that simply do not exist in the real world due to relativity. In distributed AI training, when nodes lose sync by mere milliseconds because of relativistic effects or leap seconds, it does not just display the wrong time, it causes split-brain scenarios where different parts of the system disagree on state updates. This forces costly rollbacks and corrupts model convergence before you even realize a failure has occurred. To understand why this matters for your career as an engineer, we have to look at how modern systems pretend that absolute simultaneity is real when physics says it cannot be. Researchers like Paul Borel have established that true synchronized time is a fiction because of the relativistic nature of our universe. Yet, distributed AI clusters rely on logical clocks, such as Lamport timestamps, which treat time as linear and perfectly aligned across thousands of nodes to ensure consensus algorithms work correctly. We are essentially running software that assumes a Newtonian world in an Einsteinian one. The engineering challenge is no longer just about building faster chips. It is about designing systems that can tolerate the fact that synchronized time is impossible while still simulating perfect order for training tasks to complete successfully. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This gap between physical reality and software assumptions has created significant vulnerabilities, particularly regarding how we monitor hardware in large clusters. Studies from Worcester Polytechnic Institute and UMass Amherst reveal a troubling infrastructure gap. Modern commercial GPUs often lack tamper-evident mechanisms for internal state tracking. Without rigorous telemetry using advanced primitives like verifiable delay functions or proof-of-work style checks, there are governance gaps where adversarial actors could potentially repurpose chips or bypass oversight through virtualization layers. This forces engineers to build complex software clocks on top of hardware that does not natively support secure timekeeping, creating a fragile foundation for the high-stakes workloads we run today. The irony deepens when we look at how these sophisticated systems interact with their own intelligence regarding temporal reasoning. While our infrastructure relies on nanosecond precision to keep training jobs alive, the models themselves are surprisingly lost in time. Research from the University of Edinburgh found that even advanced multimodal large language models struggle significantly to interpret visual clocks or calendars correctly. This highlights a critical disconnect. We have built systems needing extreme low-level temporal accuracy, but our own artificial intelligence lacks the fundamental ability to read a wall clock or understand a calendar date in complex scenarios. We are building super-intelligent agents on top of infrastructure that assumes they can perceive time as simply and linearly as we do, which is often not the case when they face real-world visual data. The consequences of ignoring these low-level temporal issues extend far beyond minor software glitches. They lead to systemic fragility in how distributed consensus algorithms operate. As noted by Borel, leap seconds and daylight saving adjustments are artificial constructs that disrupt the continuous flow required for systems like Fisher-Lynch-Peterson impossibility results to hold true. In AI training environments, these micro-disruptions can trigger silent failures where models diverge due to timestamp mismatches or security vulnerabilities, allow unauthorized model training on shared hardware without detection. The reliance on flawed synchronization assumptions means that a single second of drift can cascade into hours of wasted compute and corrupted data weights that are impossible to recover from later in the pipeline. For developers building distributed systems or MLOps pipelines, this represents a major shift in professional responsibility. You must stop treating time synchronization as a solved problem handled by operating system defaults. The transition from setting clocks once during installation to actively managing clock drift in real time is now a critical skill for ensuring model training reliability and data integrity at scale. Engineers need to understand that relying on Standard Network Time Protocol or OS timestamps is insufficient for high-scale AI clusters where every millisecond counts toward convergence speed and cost efficiency. The choice of hardware architecture must include considerations for clock governance, asking how the system handles drift, relativistic effects, and potential tampering without trusted firmware support built into the silicon itself. The future of scaling artificial intelligence will not just be about adding more GPUs or larger models. It is fundamentally about building better temporal abstractions that can withstand physical reality. Practitioners who learn to architect around the forward in time only, constraint and implement robust telemetry like verifiable delay functions will become essential assets for the next generation of reliable, scalable AI infrastructure. We are moving into an era where timekeeping is a first-class citizen in system design rather than a background utility. If you can demonstrate how your systems handle the fiction of synchronized time without breaking when physics intervenes, you will be solving one of the hardest problems facing the industry today. This shift changes how we approach career planning and technical judgment in AI engineering. It requires us to look past the flashy capabilities of models and understand the invisible layers that make them possible. The clock is not just a tool for telling time. It is the conductor keeping an orchestra of thousands of machines playing together without falling into chaos. As we push toward larger, more complex distributed systems, the ability to manage this temporal complexity will define which teams can deploy reliably at scale and which ones will be held back by silent failures in their infrastructure. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.